Hello friends, I welcome you in lecture number 32 on graph theory. In lecture number 31, we have taken introduction of special type of graph which is known as tree, and we now know that a tree is a graph which is connected and it has no simple cycle. A connected undirected graph with no simple cycles is called tree. And now in this lecture we are going to discuss properties of trees. We have certain properties of trees that we will discuss from this lecture. In this lecture we are going to prove one property of tree, and that property is that suppose we have a tree denoted by capital T, then this property says that if we take any two vertices, say U and V, in a tree capital T, then there is a unique, that is one and only one simple path between U and V. If capital T is a tree, then there is a unique simple path between any two vertices, say U and V, of tree capital T. And converse is also true, that if we have a simple path which is unique between any two vertices of a graph, then that graph is always a tree. So we are going to prove this theorem, or we can consider it as property of a tree, and some authors consider this as another definition of tree, or we can say that this is equivalent definition of tree. So the result is an undirected graph is a tree if and only if there is a unique simple path between any two of its vertices. So here we have two-way statements. Suppose we consider this as statement A and this as statement B, then here we have this type of situation. A implies B and B also implies A. So we first show that if statement A is true, then statement B is true, and then we assume that statement B is true and we prove statement A, because we have if and only if, that is A and B implies each other. If A is correct, B is correct, and if B is correct, A is correct. So first we will assume that statement A is true. That means we have an undirected graph which is a tree. So we first assume that suppose we have a tree which we will denote by capital T. Suppose we have an undirected graph which is a tree denoted by capital T, and we want to prove that there is a unique simple path between any two of vertices of capital T. Now because T is a tree, by the definition T is a connected graph, and if graph is connected, then there is a simple path between any two of its vertices. So all we have to prove is that the path is unique. There is one and only one path between any two vertices of a tree capital T. So that we will prove by contradiction. We will assume that suppose there are two paths which are simple between two vertices of a tree capital T, and we will have some contradiction. Again I repeat, first we assume that we have an undirected graph which is a tree denoted by capital T, and we want to prove that there is a unique simple path between any two vertices of this tree capital T. So for that we know that T is a tree, therefore by definition T is a connected graph with no simple cycles, and because T is connected, by the definition of connected graph there is a simple path between any two vertices of T. So all we have to prove is that uniqueness of that simple path. We have to prove that the path between any two vertices is exactly 1, or there cannot be more than one simple path between any two vertices of capital T. So that we prove by contradiction. First we assume that suppose there are two different paths between two vertices, say U and V, of tree denoted by capital T, and we will have some contradiction. Now because we have assumed that there are two paths between these two vertices, what will be the nature of those two paths? We may have this type of paths also, that one path is starting with U and ending with V. Suppose we denote it by P1, and we can have this type of another path from U to V. So if we have this type of situation, that the two paths from U to V are in this way, there is a path say denoted by P1 from U to V, and from U to V denoted by P2. Then you can see, if we have this type of situation, then we will have a cycle starting at U and ending at U. We will have a simple cycle in a tree capital T if there are two simple paths between two vertices U and V like this, and that will arrive us to the contradiction, because we have assumed that capital T is a tree, therefore it cannot have any simple cycles. And if we consider these two paths P1 and P2, then they construct a simple cycle starting with U and ending with U. Therefore our assumption is wrong. Our assumption was that there are two different paths between two vertices U and V. So that wrong assumption is giving us this simple cycle in a tree capital T. Therefore assumption is wrong, and therefore there cannot be more than one simple path between U and V, and therefore there is a unique simple path between U and V. So this is one possibility, or this is one structure of different paths between U and V. But it is not always necessary that the paths between U and V will look like this. We may have this type of situation also. For example, suppose we have U here and vertex V here, then we can have this type of path also. Suppose I go in this way, then U2, then suppose this is U3 and U4. Now suppose both paths which are different are not meeting at V, or suppose V is not the vertex which is common to both the paths, then they can meet at some another vertex, or there can be some another vertex which is common to both the paths. And here we will go up to V. Suppose this is one path denoted by P1. Another path may look like this. Suppose I consider this vertex as V1. Suppose we have V2 here, and these two will coincide, say V3, and from this we go up to V. So this is another path P2. So we may have this type of situation also. If we assume that there are two different paths P1 and P2 between two vertices U and V, then one possibility is simple, that paths will look like this and they will make a simple cycle. But suppose paths look like this, then also we can see that we will have some vertex after U that will belong to both the paths P1 and P2. Suppose that vertex is denoted by W, and it is not necessary that here I get u4 and v3 always. We may have this type of situation. We can have ith vertex or ui and vj minus 1 for some I and j. We may have this type of situation. So in this situation also you can see that we get a simple cycle. You can see that if I go along this path, then I can come back to the initial vertex. I start with u and I am going along this path and I am coming back to u. That means I am getting a simple cycle in this situation also. And that is not true because our assumption is that capital T is a tree. Therefore this whatever we have assumed that there are two different paths between two vertices u and v, that is not correct. And this proves that there is a unique simple path between any two vertices of tree capital T. So this we have to write systematically. I have written all these things systematically here. First, assume that capital T is a tree and we want to prove that there is a unique simple path between any two vertices of capital T, and we prove this by contradiction. So we assume that suppose that there are two different simple paths from vertex u to vertex v, that I have drawn here. Whatever I discussed, that I assume that there are two different paths from u to v. One path you can see that starting with u, then u1, u2 and so on, it is going in this direction, and here somewhere we will end with v. This is one possible path that I have written here. Another path is P2, that is u, v1, v2 and going up to v, that I have written here, u, v1, v2 and for some n, say vn up to v. So this is our assumption because we are proving this by contradiction. We want to prove that there is a unique simple path between any two vertices of T. So first we assume that there are two different simple paths between u and v. And before writing this, we have to mention that because T is a tree, therefore T is connected, and because T is connected, therefore there is a, because of connectedness, there is a simple path between any two vertices of tree capital T, and all we have to prove is the uniqueness of this simple path between any two vertices. So first we assume that T is a tree, therefore T is connected, therefore that connectedness gives us the guarantee that there is a simple path between any two vertices. Now we have to prove that that simple path is unique, or there cannot be more than one simple path, and that we prove by contradiction. And therefore we assume that suppose there are two different paths, say P1 and P2 from say vertex u to vertex v of T, and after that here I have used w. Suppose if we are going along these two paths, then we will always have one vertex w which will belong to both the paths P1 and P2. This vertex w can be last vertex u also. In that case we will have this type of situation, or we can have this type of situation also, that we are going up to v and from this we are going up to v. So this w can be equal to v also, or it can be different from v also, but it will always be there if we have simple paths between u and v. So here I have written that let w be the first vertex after u, that is after starting with u, somewhere in between u and v, we will have w. Let w be the first vertex after u, which belongs to both paths p1 and p2, and the vertex w will be v also, but at least there is such a vertex, that is w can be equal to v also, but there is always one such vertex w which will belong to both the paths p1 and p2. Then w will be equal to ui equal to vj for some indices I and j. In this particular graph, w is equal to u4 and equal to v3, that is I equal to 4 and v equal to j equal to 3, and this can be different also. So if we have this type of vertex w which belong to both the paths p1 and p2, then we can see that there is a simple cycle in a tree, and if we have a tree, then we cannot have a simple cycle. So here I have written this produces a simple cycle, and that cycle is u1, u2, u3 and going up to v1 and u, that I have mentioned here, which is simple, or you can write here also. But capital T is a tree, and so it must not have any simple cycle. This contradicts our assumption. And what was our assumption? That there are two different paths p1 and p2 between u and v. So that assumption is wrong. This contradicts our assumption that there are two simple paths between vertices u and v, and u and v was arbitrary vertices of T. Therefore, there is a unique simple path between any two vertices of a tree. So this proves first part of this result. Here we have two statements. So we have proved first part, that if undirected graph is a tree, if that is correct, then there is a unique simple path between any two of its vertices. That is, we have shown that statement A implies statement B. Now we prove that statement B implies statement A. That is, we assume that there is a unique simple path between any two vertices of a graph, then that graph is a tree. So now we prove converse part. Converse part means B implies A. So here I have written that now assume that there is a unique simple path between any two vertices of some graph G, and we want to prove that G is a tree. Now to prove that G is a tree, we have to prove that G is connected and it has no simple cycles. Now this connectedness is obvious because we have assumed that there is a unique simple path between any two vertices of a graph G. That assumption gives us the connectedness. So here I have written that since there is a unique simple path between any two vertices of a graph G is connected. So this is proved from the assumption. Now all I have to prove is that there are no simple cycles in a graph G. So that I am explaining first. I have to prove that there are no simple cycles in a graph G. Now we prove this by contradiction again. We assume that suppose there is a simple cycle in a graph G. Then if I consider this graph containing three vertices, I assume that suppose there is a simple cycle in a graph G and I have three vertices in a graph G, and I assume that suppose there is a simple cycle in a graph G which will look like this. It is starting at V1 and ending at V1. I assume that G has a simple cycle which looks like this. Now if you observe, that if we consider this simple cycle and if we consider paths between V1 and V3, then you can see there are two paths between V1 and V3. This is one path starting with V1 and ending with V3. I can consider this as one path, and another path is V1 to V3. This is another path. So if I have at least one simple cycle like this, then we can see that there are two different paths between vertices V1 and V3, and our assumption is that there is a unique simple path between any two vertices of a graph G. So that contradicts our assumption. Therefore G has no simple cycles and therefore G is a graph. Now instead of V1, V2, V3, suppose we have n vertices, then we can have this type of situation. Suppose we have V1, V2, we can have this type of situation. If I have n vertices in a graph and if I assume that there is a simple cycle from V1 to Vn, suppose, or there is a simple cycle whose initial point is V1 and ending point is V1. If my assumption is like that, suppose I have Vn here somewhere I have Vn minus 1. Okay, this will continue like this. Suppose I assume that there is a simple cycle from starting with V1 and ending at V1. So in that case we can see that there are two paths between V1 and Vn. You can see those two paths here. One path is starting with V1 and going in this direction and up to Vn. You can consider this path up to Vn. This is one path. Suppose we denote it by P1, and another path is containing V1 and Vn, that we denote by P2. So if there is a simple cycle, then that simple cycle will give us two different paths between the vertices V1 and Vn, and that is a contradiction because we have assumed that there is a unique simple path between two vertices. So therefore our assumption is wrong and therefore G is a tree. So that also I have written systematically. To prove that G is a tree, it remains to prove that G has no simple cycles, because by our assumption we find that there is a path between any two vertices, therefore G is connected, and if G has no simple cycles then G becomes tree. So we prove by contradiction. We assume that suppose G has a simple cycle of length greater than 1. Here in tree we have assumption that graph is always simple, so it cannot have loop at any vertex. So it cannot have a cycle with length 1. So therefore this is the assumption that suppose G has a simple cycle of length greater than 1, and that we denote by V1, V2, Vn and ending at V1. I have written here G has no cycles of length 1 because it has no loops. Now this cycle is simple and therefore these two will give us two different paths. Because this cycle is simple, this edge joining V1 and Vn will not appear in this path V1, V2, Vn. You can see that this edge joining V1 and Vn will not appear in this path starting with V1 and ending at Vn, and therefore the paths P1 equal to V1 Vn, I have denoted this path joining V1 and Vn by P1, and this path joining V1 and Vn by P2. So therefore the paths P1 equal to V1 Vn and P2 equal to V1 V2 Vn are two different simple paths from V1 to Vn, and this is a contradiction to the assumption which we have taken. Our assumption is that there is a unique simple path between any two vertices, and we get the contradiction because of this assumption that G has a simple cycle. So therefore G cannot have any simple cycles, and therefore G is a tree. So this is very interesting property of a tree, that an undirected graph is a tree if and only if there is a unique simple path between any two vertices of a given graph. So using this property also we can check whether a given graph is a tree or not. We can find out two different paths between two vertices to prove that given graph is not a tree. So sometimes they ask you to prove this property. In summer 2020 exam they have asked this property. First you have to write down the definition of tree, and you have to prove that there is one and only one path between every pair of vertices in a tree, capital T. So this is the first part which we have proved. We have proved that if capital T is a tree, then there is a unique simple path between any two of vertices. So they have asked A implies B, that there is a unique simple path between any two vertices if capital T is a tree. Sometimes they can ask you to prove both the parts also. So depending upon the nature of the question, you have to write down whether they have asked only one part or another part. Here they have asked to prove that there is one and only one path between every pair of vertices in a tree, capital T. So you have to assume that suppose we have a tree, capital T, then this implies that there is a unique simple path between any two vertices of tree, capital T. So this is all about this session. I have tried my best to explain this proof of this result, but still if you have any doubts you can ask in comment section. Thanks for watching.